So now we continue with the radioactive thing, and we can see the next part, that is a change in the nucleus in alpha, beta and gamma emissions. We have read that the radioactive substances are not stable. The nucleus undergoes spontaneous decay by the self-emission of either alpha, beta or gamma radiation to form a more stable nucleus. The emission of alpha, beta and gamma radiations is a nuclear change. In the emission of alpha, beta and radiations, there is a change in the number of protons and neutrons inside the nucleus, while in the emission of gamma radiation, there is only the change in the energy of the nucleus and no change in the number of protons and neutrons inside the nucleus. We understood that very well, that whenever there is a alpha radiation taking place, there is going to be the loss of 2 protons and 2 neutrons from the nucleus of the atom. Whereas when the beta particle taking place, at that time one of the neutron of that particular atom is going to convert into proton. So there will be an addition of the proton and there will be a subtraction of a neutron. Therefore, the atomic number and atomic mass in each case of alpha or beta radiation, there is going to be a change in those numbers. So that is how we are going to see now. So let's see the alpha emission. So we see the alpha emission. If I see an alpha emission for a body which is X, which has got A and Z, the atomic mass and atomic number. So on having an alpha radiation going through, so when there is an alpha radiation going through, what will happen is that the name of course will change, because it's no longer going to be X, because X is for a particular number of atomic number, but here the atomic number is going to change by 2. So you can see that the mass is going to change by 4. So it will be, mass will be changing by 4. So it will be A minus 4 because of the loss of the helium. So what you have seen, that there will be a loss of a helium atom, the nucleus, that is 4. That's why this 4 is subtracted from A and 2 is subtracted from Z. So accordingly, after the emission of an alpha particle in X, the atomic number reduces by 4 and the atomic mass reduces by 4 and the atomic number reduces by 2, and a helium nucleus is going to be given out. This is a kind of a chemical equation we can write, or not chemical, but a nuclear equation we can write for the emission of an alpha particle. So if an unstable nucleus contains much more neutrons than the number of protons, it can emit a particle containing 2 protons and 2 neutrons tightly bound together, known as alpha particles. A stream of alpha particles is called as alpha rays. So that's what they are saying, that if the number of protons and the number of neutrons is quite different, if the number of protons and neutrons, there's a huge number of difference between the two, it becomes an unstable nucleus, and such an unstable nucleus is going to emit out 2 protons and 2 neutrons out of it as a decay, and that is called as an alpha particle, and such stream of such particles are called as alpha rays. If the nucleus of X of a radioactive element of mass A and atomic number Z emits an alpha particle, the daughter nucleus Y of the new element is formed, which has the mass number equal by A minus 4 and the atomic number equal to Z minus 2. Thus, due to the emission of the alpha particle, atomic number Z decreases by 2 units and mass number A decreases by 4 units. This change can be expressed in the form of the reaction as AXZ is going to decay to A minus 4Y Z minus 2 plus 4 He2. The resulting nucleus has 2 protons and 2 neutrons, total 4 nucleons less than the original or parent nucleus. Example, when the radioactive uranium 23892U, so it is U23892 on alpha radiations, it is going to become 23490, and it is going to become, instead of uranium, it will become thorium. So it is going to be thorium because 90 is for thorium plus 42He. So a new nucleus thorium 23490 thorium is formed, and the chain is represented as 238 uranium 92 is going to become 234 thorium 90 plus 4 He2. Got it? So this was about alpha particle. We now move on to the beta emission. When an unstable nucleus contains neutrons with then more than their protons, a neutron may change into proton by emitting an electron for charge conversion. The electron given out from the nucleus at a high speed is called as the beta particle. So we very well know that the beta particle is nothing but the electron given out by the nucleus of the atom in the form of neutrons. Case दो part बनेंगे, one proton and one electron. Electron is released by the nucleus in the form of beta particles. The change can be represented by the following equation. So the equation what will be there for beta will be this way. It will be x a z on beta radiation which is going to take place. It will be seen that A will remain A. The mass does not change. The mass does not change. Why does the mass not change? Because the number of proton plus the number of neutrons is going to remain the same, because only difference is that one of the neutrons is getting converted into proton. So there is an addition of one in proton but subtraction of one in neutron. So the total number of nucleons still remain the same. So the mass still remains the same. That's why it is going to still remain the same mass. So it will be as Y, but this is going to be A, but this is going to be Z plus 1. Because the atomic number is going to increase by 1, so it will be Z plus 1 plus 0 E minus 1. So this will be the particle, that is the beta particle given out, that is 1 electron. Okay, they have given it in this form, that is, instead of taking X this way, they have taken it as 1 neutron, which is like this, on particle beta given out. It will become 1 proton with 1 plus an electron over here like this. Okay, this is just a nuclear reaction, not the element ka reaction. So that is the difference between the two. Anyway, we will require both of, we will require this one as such. This was just for understanding that what will happen to a neutron. The change can be represented by N10 giving out 1p1 plus 0e minus 1. A stream of beta particles is called as beta rays. Note, later on, to keep the number of particles either odd or even or both sides, another particles called anti-neutral was also assumed to be emitted along with the beta particles. This particle is uncharged and its rest mass is 0. But then the particle transformation equation becomes, so it is just that to keep the number of particles either in odd or even, though that is one more. Anyway, I think it is not required for you to understand it is anti-neutrino karke aata hai, that is just V. So one more addition is going to be there at the end of the equation, so that is 1B, but we are not going to consider that thing, so don't worry. Thus, in the emitting of beta particles, the number of nucleons in the nucleus, sum of protons and sum of neutrons remain same, but the number of neutrons is decreased by 1 and the number of protons is increased by 1. In other words, the emission of beta particles, the mass number A does not change, but the atomic number Z is increased by 1. The change into a new nucleus of element with properties similar to those of the element similar to those of an element one place higher in the periodic table. Okay, we can see that after it has got a beta radiation given out, the properties of the element are going to change by one place higher in the periodic table. It changes in the new nucleus of element with properties similar to those of element one place higher in the periodic table. The daughter product is thus an isobar, same mass number but different atomic number of the parent atom. If the radioactive nucleus P with mass A and atomic numbers Z emits a beta particle to form a daughter nucleus Q with mass A and atomic number Z plus 1, the change can be represented by APZ, that is I have written as X, so I will make this as P, APZ beta particles give you A Q Z plus 1 plus electron. Example, the radioactive carbon nucleus 14C6 having 14 nucleons, 6 protons and 8 neutrons emit 1 beta particles and change into new nucleus nitrogen 14N7 having 14 nucleons, 7 protons and 7 neutrons. The change is represented as follows: 14C6 gives you 14N7 plus 1 electron. So that was about electronic thing of beta particle. Now we move on to the gamma emissions. In many cases, alpha and beta radiation emission is found to be followed by a gamma emission. It occurs when the daughter or the parent nucleus is in the state of excitation, that it has got excess of energy. This extra energy is released in the form of electromagnetic radiations known as gamma radiations or gamma ray photon. The gamma ray takes no mass and no electric charge from the nucleus, that is, no neutrons or protons are lost. Hence, the nucleus does not decay into a different nucleus. That is, there is no change in the mass number A and atomic number Z of the nucleus in gamma emission. The gamma emission is represented as follows: AXZ. So it is just simple way that AXZ on emission of gamma remains AXZ plus gamma radiation. So that is just the gamma radiation which is going to be given out by the same thing. So here the star indicates the excited state of the nucleus, thus in gamma. So here they put a star over here. The star is indicating that it is in excited state. The excited nucleus comes to its ground state. Note, the electron emitted in beta radius decay does not exist in nucleus. It is created as a result of decay of one neutron into proton inside the nucleus and is instantaneously emitted. It is not possible for electron to stay inside the nucleus. So, because it is not possible to stay inside the nucleus, so emission of the energy with the time is simultaneous. It is going to be a simultaneous process. So, the electron emitted by decay does not exist in the nucleus. In a single radioactive decay, alpha and beta particles are never emitted simultaneously. It will never happen that alpha and beta both are getting emitted simultaneously. It will be either of them appearing that. There will be either an alpha or a beta which can be accompanied by a gamma emission. Gamma can occur with both alpha or beta emission. The daughter products after the emission of the either alpha particle or beta particle may again be radioactive and may further decay by emitting either the alpha particle or the beta particle. This process continues till a stable nucleus is formed. So, till what time will it happen? That अगर समझो यूरेनियम में तो थोरियम होगा, फिर आगे करते करते छोटा छोटा होते जाएगा. Till the time it is becoming a stable atom. So, it will keep on radiating out till the time it becomes a stable atom. The table below shows the effect of atomic number and atomic mass number A due to the emission of alpha, beta and gamma. So quantity Z in alpha decreases by 2, and A decreases by 4. In beta, the Z increases by 1 and no change in A. In gamma, no change in our A or Z. Now we see about the uses of radioactivity or radioisotopes. The isotopes of some elements with atomic number Z greater than 82 are also found to be radioactive. They are called radioisotopes. The nucleus of the atom becomes radioactive when number of neutrons in the nucleus exceeds the number of protons inside it. For example, Z less than 82. I thought, okay, I just made a mistake while reading it. So yeah, whenever it is not necessary that only those elements which has got we call it the heavier elements which are having the atomic mass number more than 82 are going to be radioactive. There are many such elements which are having the atomic number less than 82 and still they are radioactive in nature. So they are called as radioactive isotopes. The nucleus of the atom becomes radioactive when the number of neutrons in the nucleus exceeds the number of protons inside it. For example, cobalt 60, cobalt 60, that is 60, cobalt 27, that is Z is 27, A is 60, carbon 14, C6, Z is 6 and A is 14, potassium 40, K 19, that is Z is 19, A is 40, phosphorus 32, P 15, Z is 15 and A is 32, etc. are radioisotopes. The radioisotopes are also prepared artificially by nuclear transmutation. They find their vital use in medical, scientific and industrial fields. So first let's see the medical field. Many diseases such as leukemia, cancer, etc. are cured by radiotherapy. Gamma radiations obtained from cobalt 60 are used to treat cancer by killing the cells in the malignant tumor of the patient. For radiotherapy, radiation must be able to penetrate the human skin. The salts of weak radioactive isotopes such as radiosodium chloride, sodium ion, radioiodine are used for diagnosis. Such radioisotopes are called as tracers. These tracers are used to detect the suspected brain tumors and blood clots before they become dangerous. So they are basically tracers which are going to be injected into the blood because they are going to give out some emissions. So that's why they can easily be tracked that where exactly they have reached. So the point where they are getting blocked, you can identify those blocks and you can treat that particular blocks so that the blood flow into the body in the different parts of the body is going to be easily monitored and can be sorted out. So this is how the tracers are going to be helpful. The tracers are also used to study the natural process in the human body. For example, radiosodium chloride is injected in common sodium chloride in the human body, and the radioactivity of the blood at different parts of the body is tested to study the blood circulation. The process is called as radiocardiology. Gamma rays emitted by the radioisotopes are used to sterilize bandage, dressing, syringes, and other equipments to make them germ-free. This method is quicker, more reliable and cheaper than the process of sterilization by heat. Then we see the scientific uses. Alpha particles emitted by the radioisotopes are used for projectile for nuclear reactors. The scattering of the alpha particles from the nucleus helps in estimating the size of the nucleus and in understanding the nature of nuclear forces. So alpha particles are used for as a kind of a projectile for the nuclear reaction to take place. For the nuclear reaction to take place, alpha particles are bombarded that way. So that is how it is being used. The radioactive tracers are used in agricultural science to study the growth of plants by using a particular chemical manure. For example, to know how readily a plant takes in phosphate and to which part of the plant the phosphate goes. Third, the age of excavated material of archaeological importance, rocks and hence buried plants is estimated by the study of rate of decay of carbon 14. That is the remains of dead end plants. The process is called as carbon dating. So carbon 14 is a carbon dating compound. Industrial uses. Radioisotopes such as 235 uranium are used as fuel for the atomic energy reactors. Radioisotopes are used by engineers in factories to avoid accumulation of charge on the moving parts of the machine due to friction. The radiation emitted by the isotope ionizes the air. The ions so produced take away with them the charge accumulated on the moving parts. The ionizing effect of radiations from the radioisotope is used in making certain luminescence signs. Yeah, illumination boards. उसमें भी थोड़ा लगता है. Knowing the penetration power of the beta radiation emitted from the radioisotopes, they can be used to control the thickness of paper, plastic, and metal sheets during their manufacturing. So these are some examples of the uses of the radioisotopes. You can learn some part of it, in short, because there have been questions about the uses of the radioisotopes in different board papers, but not in detailed things. So you can just note about the simple one line points of each and every part. Now let's see the sources of harmful radiation. The main sources of harmful radiations are radioactive fallouts of the nuclear power plants, nuclear waste, and other sources such as cosmic radiations and X-rays. Radioactive fallouts from the nuclear power plants. So we know that nuclear power plants are going to use the radioactive substances, and these radioactive substances, if they are not controlled well, they can cause a disaster or cause problems to the nearby places. So the nuclear power plants are now a major source of electricity in the world. If somehow there is an accident in the reactors of the power plant, a large amount of radioactive material and radiation will escape out into the atmosphere. This will not only affect the population around the plant, but will also affect the life at far off places where they will reach due to the air currents. 3 such accidents have already occurred in USA in 28th March 1979, in Ukraine, USSR on 26th April 1986, and in Japan in 11th March 2011. These accidents caused damage to the reactor building and injuries to the person working in the plant as well as to the person in the vicinity. The next is nuclear waste. The fuel rods used in the nuclear power plant reactors are rejected when their activity decreases below a certain level. They then become nuclear waste. These rods are still quite radioactive and are the source of harmful radiations. Therefore, they should not be dumped in open garbage. They can contaminate water and soil and affect the human and living organisms. See, the rods, the uranium rods or the rods which are used in the nuclear reactors, they are going to be active only for a certain period of time. Once they become inactive, that means the radiation which are given out by them is not sufficient enough for the energy giving out will not sufficient enough, then they need to be discarded. But when they are discarded, it is not completely safe. What happens is they are still giving out the radiations. No doubt the radiations are not sufficient enough for the use in the nuclear reactors, but they are still giving out radiations, and these radiations are harmful radiations. So they cannot be discarded just in the open in the public, so like any normal garbage bin. It has to be properly discarded because they can affect the water bodies, they can affect the soil or the humans. So that's why it is very dangerous and hence to be discarded in a proper manner. Other sources are the cosmic radiation and X-rays. The cosmic radiation from the sun enters the Earth's atmosphere from the outer space. They contain a large number of high energy particles, out of which, although the charged particles are deviated by the Earth's magnetic field, but a substantial amount of uncharged radiations such as the gamma rays and X-rays reach the Earth's atmosphere. Some of these radiations are harmful for the human beings. Apart from this, the high energy particles accelerators also produce the harmful X-rays. So yeah, the X-rays and all we have understood in the spectrum that the rays from the sun, they have got the complete spectrum which also contains the gamma rays and the X-rays in it, and so that is going to be a problem. That is cosmic rays which is going to be harmful, but the quantity what we are getting is not so damaging part, so not to worry about. Harmful effects of radiation. Now let's see what is the harmful effects of the radiation. The radiation produced in nuclear reaction includes alpha radiation, beta radiations, neutrons, gamma rays and X-rays. They interact with the living tissues within 10⁻14 seconds and cause biological damage. The biological effect of the nuclear radiation are of 3 types. Short-term recoverable effect like diarrhea, sore throat, loss of hair, nausea, etc. Long-term irrecoverable effects like leukemia and cancer, and genetic effects. The first and the second effects are limited to an individual who are actually exposed to the radiation, while the third effect appears in the later generation of the person exposed to the radiation. The gene in this cell get modified or mutated. So you can see that the radiation can cause harm, which could be either a short-term thing like diarrhea and all, जो थोड़ा short में time में खत्म हो जाएगा. Medium like leukemia and cancer that will be affecting the life of the person. And the third one is when it is genetic disorder is going to be created, which is going to go from generation to generation. So there are the 3 kinds of defects which can be formed by the biological damage which can be formed by the radiation. The exposure to radiation can be acute if there is an accidental burst of radiations from an unshielded source. Similarly, It is chronic in case of person working in atomic energy establishments when they get exposed to such radiation. The exposure of pregnant women to X-rays for a long time may affect the child in the womb. It increases the risk of cancer by 40%, of tumor and nervous system by 50%, and leukemia by 70%. The exposure of the upper part of the body to X-ray may damage the thyroid glands and can cause cancer. So you can see there are different ways. 40% tumors may cancer risk of cancer by 40%. Tumors and nervous system by 50%, and leukemia 70%. So accordingly, there will be the kind of effect will be given by the radioactive material on the body. The exposure of gamma rays destroy the cells of the body and affect the blood cells, gastrointestinal tract, reproductive and hair cells. It can harm the DNA and RNA of the living cells also. And you can see hair cells का तुम लोग को idea आ ही जाएगा, because once anybody goes for a chemotherapy in cancer treatment, he loses his hair. So it is very commonly seen over there. Why is that so? Because of this radiation. So the radiations which are killing the cancer cells of the body are also killing the good cells of the body, and that's why the person becomes weak and also loses the hair from his body. The uncharged neutrons also cause biological damage. Okay. The safety precautions while using the nuclear energy. We have read that nowadays electricity is also generated by the use of nuclear energy obtained from the nuclear power plants. In the nuclear power plant, a radioactive source such as uranium-35 or plutonium-239 is used, and the control chain fusion reaction is carried out in this process. The following aspects require special care: establishment of the power plant, handling of radioactive material, and safe disposal of the nuclear waste. So let's study them one by one. First is safety measures while establishing a nuclear power plant. While establishing a nuclear power plant, generating electricity, following precautions may be taken. Ensure that the people working in it are not exposed to nuclear radiation, and in case of any accident, there is minimum spread of the radiation. So first of all, the safety of the people who are working in that particular area. So they need to be prepared, they need to be well protected. The nuclear reactor of the power plant must be shielded with lead and steel walls so as to stop radiation from escaping out from the environment, out to the environment during its normal operation. So yeah, when the normal operation is taking place, it should be seen that the radiations are not being given out into the outside, and that is done by reinforcing the whole area, making the whole area by thick walls of concrete and even lead or steel lining. The nuclear reactors must be housed in an airtight building or strong concrete structure which can withstand the earthquakes, fire and explosion. Yeah, that is very important, because if they are not able to withstand the earthquakes or fire, then automatically a damage can easily be caused to the nuclear reactor and that particular building, and it will cause a damage to the nearby places very easily. There must be a backup of cooling system of the reactor core, so that in case of failure of one system, the other cooling system could take its place and the core is saved from overheating and melting. See, the heat given out by the radiation is so high that in case if it is not controlled and it is not quenched properly, it could really burn up the whole place. So that's why there needs to be a very good cooling system. Not only that, that cooling system also should have a redundant system, a secondary system, which can be used in case of any problem with the first one. So that's why there has to be a backup cooling system available in that particular reactor. Then comes the safety measures while handling the radioactive material. People working in the radioactive material are required to follow strict and safety measures given below. They should put a special lead lining apron and lead gloves. So yeah, they need to have a lead apron and a lead gloves so that the rays are not penetrating through them and not entering their bodies. They should handle the radioactive material with long lead tongs. So they will be not standing just and ऐसे पकड़ के उसको नहीं use करेंगे. They will use a long lead tongs. So उसको पकड़ के यहाँ से ऐसे उठा के ऐसे डालेंगे. So lead tongs लेंगे and they are going to do it that way. The safety limit of each type of radiation is known. Therefore, care must be taken to ensure that no one is exposed beyond the safety limit in any case. For this, special film bags are used which are tested from time to time to know the amount of radiation to which the particular person has been exposed. See, the employees over there, they need to use a badge. So a badge is going to be put to them, and that badge is regularly monitored. So when they come to know, the badge is going to indicate how much amount of radiation that is already been absorbed by that person. So if it goes to slightly, it reaches the safety limit, automatically that person is withdrawn from that particular, that work and shifted somewhere else, and a new person has been deployed over there. So of course he's not going to lose his job, he's just going to be deployed for some another work. So it is seen that no person is going to be continuously affected by that particular radiation. For that, the special badges being used. The radioactive substance must be kept in the thick lead container with a very narrow opening so as to stop radiation coming out from other directions, such that it absorbs the radiation which strikes on its wall from the inside. Alpha particles can easily be stopped by thin metal sheet, but a beta particle need a thick metal sheet, whereas the gamma ray need a very thick lead sheet. So that is why we are going to have it in a container, a box which will be a lead container, so that it can be given out only from one particular opening. It is not going to be coming out from all the directions. Safety measures in that safe disposal of the nuclear waste. So yeah, disposal is very important. The radioactive material after its use is known as a nuclear waste. The nuclear waste obtained from laboratories, hospitals, scientific establishments or power plants must be first kept in a thick cask, and then they must be buried in the special constructed deep underground stores. These stores must be made quite far from the populated area. The cask can also be buried in useless mines, and these mines must be sealed after storing the cask. So you are basically avoiding any human contact of that particular that is nuclear waste from the people. So that's why you are using very old mines, or you are using some different cave like things, the underground stores, for which is the material is stored in a cask, a thick metal cask. Lastly are background radiations. The background radiations are the radioactive radiations such as alpha, beta and gamma, to which we all are exposed even in the absence of actual radioactive substances. So even if there is no actual radioactive around it, but right now also when you are standing or sitting, you are being affected, or you are being undergoing the background radiation. So there is background radiation being affecting you. But of course the quantity is so less that it is not going to affect your body at all. Sources, there are two sources of background radiations. The internal sources, the radioactive substances is potassium K40 and carbon 14 and radium present inside our body. So that is the potassium 40, C50 are present in our entire body, and they affect all parts equally, while radium is large found in the bones, and it is affected only the bones and the reproductive organs. The next is the external source, cosmic rays, naturally occurring radioactive elements such as radon-222 and solar radiations. So that is the cosmic rays also has got the radon-222 and solar radiations. It is not possible for us to keep ourselves away from the background radiations, but the total background radiations from both the internal and external sources do not exceed the maximum permissible dose for human safety, so we need not worry. So the effect of different radiations of human tissue is measured in a unit called sievert, okay, SIEVERTS, sievert SV dose. In one exposure of X-ray for chest, the patient receives 0.2 millisieverts dose of radiation. So that is what you are going to get when you are having a fracture or something and you are going for an X-ray. So that is about the background radiation. So that was about the first part of the chapter regarding radioactivity. So this was quite an easy one. Yeah, it has no numericals as such, but there will be certain kind of questions which can be asked based on these particular kind of equations what are there. So these equations are very important, and accordingly you can check up the questions in the solved examples over here. In the solved example, you can see from question number 9 onwards, there are these questions which are related to these particular kind of equations. So question number 9, 10, 11, 12, 13, these are the ones which are the important kind of the numerical sort of questions which are based on this particular thing. And in the exercise part, you can see again on Yeah, after 29. So 29, 30, 31, 32, 33. They are the 30, 34 and 35 also. They are the ones which are connected. In fact, further bhi hai, aage bhi hai. So all these are questions which are related to such equations wherein you can easily find out that what will be the resultant material be having the atomic number and atomic masses after the alpha, beta and gamma radiations. Okay, so this was about the first part of the chapter. Now we move on to the next part of the chapter in our next video.